Okay, so we're going to try to redo the conversation about permutation tests. As you guys remember with class on Tuesday, it was a little bit chaotic, so this is going to be an abbreviated video, but also a tutorial of the different steps that we did so that you can understand permutation tests relative to parametric and non-parametric approaches. As a reminder, both parametric and non-parametric approaches have their own pros and cons. Parametric approaches like a one sample t-test, a two sample t-test, what we will do later in terms of ANOVAs and regressions. They have particular requirements. More or less often, they have to have data independence. There are some exceptions to that, like pair test. More importantly, they have to demonstrate normality. They have to have that bell-shaped curve. In addition, they have to show homeoscedasticity. Homeoscedasticity being that the varying structures of your different samples are the same. Heteroscedasticity means that the variation is different. So as an example, if you have two samples and they have roughly the same range, same standard deviations, that's homoscedasticity. If you have one sample where there's very little variation, you have a second sample where there's a lot of variation, that's heteroscedasticity. Homoscedasticity and normality are two of those basic assumptions. When you meet those assumptions, you could use the calculus of a normal distribution to generate p-values. P-values which allow you to tell you whether it's going to describe the random or non-random pattern. Great. If you don't, you can do something like a non-parametric test, like a Mann-Whitney-U test, like a Wilcoxon sign rank test. Wilcoxon sign rank test, as we know, is beautifully simple and straightforward. That's Melody in the background. She's very nice. She actually brought my lunch because I'm an idiot. I left it in her office.
And because I love him, I didn't eat it.
She did not eat the lunch, which is very, very nice. Thank you, Melody. So non-parametric procedures are useful when you don't meet those assumptions of normality or homoscedasticity. But one of the things that they do is they rank the data. We've talked about that. And ranking is not a terrible thing, but it's a weird thing, one. And two, it takes away so much of the structure of your data by creating a uniform distribution that goes from 1 through n, where ties have to be averaged, 1, 2, 3, 4. So if you have very little differences, all of a sudden they become huge and profound. If you have very large differences, all of a sudden they become sort of lost and muddled. It works, but you can kind of see where it doesn't seem like a very useful way of structuring the data. A third option, and from now on we will teach all three options with each of our procedures when available: parametric, non-parametric, and permutated. Permutated is the third option, and there's a few benefits to permutated before we describe what permutated is. One, a permutated test is analogous to the test that we're using, like a two-sample test. But what permutation does is, instead of requiring conformity to the calculus of a normal distribution, or restructuring the data so it is ranked and uniform, what permutation does is it basically takes your data, it evaluates any potential pattern within your data. It then runs n iterations of that data again, but each time it resamples the data and therefore creates a new set of associations and looks whether these resampled randomized data sets are more extreme or less extreme than what you actually measured. So one of the nice things about this is our p-value is literally the number of times, or the proportion of times technically, that what you measured is more extreme than randomizations of those data points. Now that might sound a little bit confusing right now, and that's fine. But the concept is actually pretty freaking brilliant. A few things that I like about it, not least of which, is the analysis you do is based on the distribution that you measured. So it's not forcing a normal distribution. There are some caveats that make it a little bit weird, but for the most part, it's really a robust system to actually evaluate the data relative to the structure of the data that you have. Okay, so what do we mean by randomization? Well, randomization is a process by which you can simulate a final result based on randomizing distribution of data points using some form of an approximation, like a Monte Carlo approximation. And what you're looking at here is you're looking at a GIF file that shows you individual data points that are randomly placed along the x and the y axis. What you're looking at is you're looking at the curve, and if you remember the curve, the ratio between the diameter circumference is 3.14, i.e. pi. And if you create that curve within this array, as represented by the red area, what you can see is you increase the number of data points in it, your ability to approximate pi becomes ever more correct. And really, I mean, it's a truly robust way in which you can sort of get at something that, as we know, what pi is actually infinite. You can't get rid of it, but you can get an incredibly precise approximation of it. So that's essentially what we are doing. Now, what we're going to use is we're going to use this Butterfly Edge dataset. This Butterfly Edge dataset was a project that students did on campus for 5, 6, 7 years. I really don't know. I could look, but I didn't. And they walked this very specific transect. 5 were in the urban area of the campus. 5 were in the conservation area of the campus. And in this dataset, what we're looking at is we're looking at the diversity of butterflies relative to whether a particular location on the transect was in the interior of the transect, so like only urban or only conservation, or was it along the edge, an area where you're transitioning between two different habitats, like the transition between an urban to conservation area. If it's interior, it could be in the middle of the academic area of the campus, or it could be in the middle of the woods. If it's edge, it gets right along that border. Okay, so as we look at those data, we see things like this. So for each of these, we have samples, and for each of these, we have the habitat, interior, or the edge. And then what we have here is we have the average biodiversity for each stopping point in the transect where biodiversity of the butterflies are measured. That measurement was relatively straightforward. Basically, the student got to a particular point, 50 meters intervals, stopped for a minute, scanned the environment for any butterflies that may be present or moving past that location, identified the species, and determined the number of individuals. And what you get here is the average. So for the average of this first sample, all the interior locations was 0.5. The average for the second interior was 0.2. The average for the third interior was 0.83. The edge, we have the same basic thing. The first edge, which is our 45th ID, but the first edge, there are no butterflies present. The second sample for edge, there was on average 1 butterfly present. The third one, 0. The fourth one, 0.5, and so on and so on and so on. What we can do is we can take this information. Let's actually save this, and let's go into Dropbox, and let's open up our, no, that's my chair position. Go into teaching, go into biostats, go into our year, go into our project. And I'm going to make a new folder, and I'm going to call it 7D. I'm going to call it permutated. And inside that folder, I'm going to make a data file, and I'm going to save the CSV, and we're good there. And then we're going to go to R, and we're going to open up a new project, which we've done many times before, And I'm going to go to that folder, and remember, I'm going to the folder that has everything, right? 7 permutated, and I open up that. As you'll notice, our data folder's right there, and our file's right here, but we need to create those other 2 folders. So I'm going to create my code, and I'm going to create my output. That's pretty good. Okay, so we have our data. What we need to do is we need to import it. So I'm going to go over, and I'm going to get a file that maybe we've used recently here, and that should actually help us. Let's do sample 1. I'm going to copy all of that. I'm going to create a new script. That didn't work. Let's try this again. That did work, and I'm going to delete a bunch of information we don't need. We're going to fix that. We're going to keep this. Get rid of that question. Get rid of these results. I'm going to get rid of these values that we did before. I'll keep the plotting for the time being because we're going to come back to that. And okay, now we have the basic stuff we need. So let's save this file. We're going to save as, and we're going to go into our code, 7D, and this is butterfly. Okay, great. So we run our lines. We get our data. We import our data. Then take a look at here, and we have 3 IDs, so we really don't need, well, we're going to keep ID. So we're going to get rid of this line of select because we're going to use everything. But we need to change habitat, and we need to make that into a factor. Okay. And then butterfly biodiversity we want as a number anyway, so that we're going to keep that there. And if we want to take a look at it, this is what we look at. Sorry. That's what we look at, exactly what we saw before. We save this again. We have our data in here. We run it. We check the summary. Our habitats are correct. 40 edge, 40 interior. The order seems fine. It doesn't matter which one is first, and edge seems very appropriate. We attach in this case. Okay, so now we have to do some modification. We can do a normal t-test. So we do butterfly, biodiversity, by habitat. And we do DF. We'll keep that. Well, we'll get rid of that. We don't really need this right now. Okay. So we run it. We get our results. We have a very small p-value. When it's a small p-value, we describe the alternative. So it looks like there's a difference between them. We can sort of figure that out down here by looking at the means, but I like to use plots. So let's actually make our plots. And we're going to make a GG plot. So we'll get rid of that part. We're going to go here. And we're going to do our x-axis, which is habitat. We're going to do our y-axis, butterfly. Biodiversity, we're going to get rid of habitat. That's good. These are aesthetics. And those look good. And we got a new system in our environment. That looks good. And this.
I'm having trouble understanding.
Habitat. And butterfly, biodiversity. We don't know what our title is yet because we don't have a result sentence, but we do know we have some information here, so we can put that in if we want to. And our p-value is equal to 0. Oh no, it's actually less. And our degrees of freedom. Kind of weird, but remember that's if we don't know whether we have heteroscedasticity. Okay, so we can write that in. We can take a look at it. We're going along. I'm gonna make this a little bit wider now so we can see our plot. Oh, okay, there we go. And yeah, that looks good. I mean, it kind of looks like edge is more, and that's great. But notice that the variance structures are not equal. They're definitely not equal, 1. And 2, these don't really look normal. I mean, maybe interior is normal. That actually looks normal. The median's kind of in the middle. The 25th to 75th percentile is pretty good. The range is pretty good. That is pretty narrow for the lower quartile range, but the upper quartile range kind of spreads out, so maybe a little skewed. But the edge definitely looks skewed. The median and 25th percentile are the same. The 75th percentile is way up, and then it seems to skew up. So we need to actually test for normality, because that t-test may not be appropriate. So I'm going to go back up here, normality test. And we could do t-apply butterfly, biodiversity, by habitat, and Shapiro test. We can do that. And let's do another t-apply by butterfly, biodiversity, by habitat, by, let's go, let's do histogram. And let's do the last one. I think it is, but I'm thinking I'm going to mess this up. It's QQ plot. Let's find out, because I actually don't remember. QQ plot. Nope, that's not what I want. That's what I want. Okay, so it's lowercase QQ. QQ plot. Let's run these. Okay. So our Shapiro test, well, the edge, that is a small p-value. That's suggesting it's not normal. The interior has that border p-value, but it's kind of suggesting not normal too. So that's not looking good for us. If we want to go here, and I'm actually going to open this all the way because we want the plot function down underneath. And I'll get my pretty face back in a second. And we look at our histograms. Well, for edge, that is definitely skewed. For the interior, that's looking pretty skewed. And I'm actually going to get our par MF row equals C, and then we want 1 row, 2 columns. Let's do that. Okay, yeah, these are looking pretty skewed. And if we do our QQ plot, they are definitely not aligning very well with the sort of, the expected blue lines. So these data are not normal. I'm going to write down an issue. normal. So now we have a choice. Our choice is we could do a non-parametric test. But again, the non-parametric test has that problem in the sense of what we're doing is we're now ranking everything, and that's kind of weird and kind of ugly because the difference between these two numbers is very small and much smaller than a whole number unit. So we can randomize. Randomization is what we're going to do is we're going to take our measured values. This is what we actually measured. Each one of these is associated with a specific habitat from a specific sample. What we're going to do is we're going to take those measured values and we're going to randomize their order and reassociate them with a different habitat potentially and sample. So we're going to resample. So let's call this first one RR1, we'll call this habitat, we'll call this RR1, and we'll call this butterfly biodiversity, BBD. Okay, so to randomize, we can do this in Excel pretty simply. We basically create a function, that's rand, open parentheses, close parentheses. That will give us a number that ranges between 0 to 1 based on a uniform distribution. And each time that we rerun it, we get a new number. In fact, each time we do anything in Excel, we get a new number. We need to create a random number for every single row. So I copy and paste it in. Because this function changes every single time I do anything, what we need to do is we need to change it from a function to a value. So I copy, and then I do Control, Command, V, and I save it as a value. And that now changes the number from a function to a value. And that's great. I take our numbers, again, this is what we measured. I paste that here. And then what I'm going to do is I'm going to resort by column D so that these numbers in columns E get reordered. They get reorganized based on the random number. So I do that. I go over here. I do habitat. Great. So now sample 1 is not 0.5. It's actually 1. Sample 2 is not 0.2. It's 0. Each of these numbers were measured, but they've now been resorted elsewhere. And now I want to associate those biodiversity randomized numbers with the actual categories. Okay, there we go. Sometimes Excel can process a little bit slowly so it doesn't look like it's right. Now, when we do a permutated test, we don't do that once. In fact, we don't do it twice. We don't do it 3 times. We do it hundreds upon thousands upon, let's see, 5,000 to 10,000 times. And what we're going to do is we're going to compare each one of these randomized redistributions with what we originally measured. So what does that actually look like? Well, an example, and I did this a little bit further, is here, where we have each one of our randomization pairs. So this is our first one, where these numbers were randomized relative to the samples. We have our second one. Again, it's the measurements, but each one of these measurements is randomized relative to our samples. Then we have our third one. This is just a sample, so we're only doing this 3 times, where again, when we actually do this in R, we'll do it for 5,000 to 10,000 times. When we save this file, let's actually save that file now, and we'll go over to our data, and let's make sure I'm in the right place, if that's looking good. And we go into data. I'm going to actually call this randomized. And I'm going to go back into R. And R is good, but what I'm going to do is I'm going to switch this over to, let's save this file, okay, and I'm going to copy everything here, and I'm going to open up a new script, and I'm going to paste there if I'm lucky. Nope. I'm going to try this again, paste a new file, and I'm going to call this new file, save as, and I'm going to call it butterfly D, but I'm going to call it randomized. Okay, and we'll fix this in half a second. And we'll have to fix our mutations, and we're going to delete out this stuff for right now because we don't need it. And okay, that's looking good. So we have to reload our stuff just like we did before. That's weird. I don't know what that is. But we load our packages, that's fine. We have to get our new CSV file, and that's when it's randomized. That looks good. We import that. We get our summary. We have to fix these variables. So let's go over here, down to mutate, and let's switch out, and we're going to go R1 habitat equals as factor R1 habitat R2 habitat equals as factor R2. Oh, I see. Oops. R3 habitat equals as factor and we need a final parentheses, so we have all of our parentheses, they're closed off, life is good. Okay, so we minim all factors from line 13 through 17. We run that. We run our summaries. Our summaries are looking good. Habitat, R1, R2, R3. And we could do attach. That's fine. That's fine. So we're going to do attach. Okay. So now what we could do is we could take this exact same thing. We do our, our t-test. And again, we get the same p-value. That doesn't change. That's the actual butterfly biodiversity relative to habitat. But now we're going to actually do simulated t-test. And we're going to take this exact same equation, but we're going to have to modify it. So instead of butterfly biodiversity, let's do R1, BB, and then we're going to do R1, habitat. Okay, that's looking good. Let's collect this again. We're going to do R2. I'm just going to copy out some things, change up the values, and then we're going to do R3. Okay, so this is the p-value we got when we actually did our measurements. When we do a simulation, we're going to run the same test. And what do we not have? Why not? I got a little typo somewhere, obviously. R1BB, that's there. R1BB, right there. It's right there. Okay, so I got another idea. Let's do our DF dollar sign. Let's see if we get it now. Well, that's just brilliant. Sometimes you got to go back, see if you can figure out what your issues are. And there's something silly, obviously. Let's sweep out that because we don't need that. We run our summary. Again, we have some issues there. And our DF. Our attach. Everything's masked. Okay, that's all good. That's working. Okay, so I've got another idea. Let's do this. Names DF. Sometimes you might just have a little typo. So I copy that out. Oh, because I do have a typo. It's R and R. So again, sometimes you're an idiot. I had two R's instead of one R, and I failed to see that. So now, we do names. Names actually just shows you what your variable names are, and sometimes when you have weird typos and you can't figure it out, I generally jump on there. So, look at that. We got to debug a bit. We run this. We have a p-value. Notice the p-value for our first randomization is 0.3. The p-value for what we measured was 0.00029. The p-value for what we measured is much smaller than the p-value for what we simulated. In addition, and this is where the permutation actually compares, the t-stat for what we measured is much larger than the absolute value of the t-stat for the simulation. So what we measured is more extreme than what we randomized. We can do that again. And again, we have a p-value of 0.1. We have a t-stat of 1.5. Against what we actually measured, the simulated t-stat is much, much smaller. In addition, the p-value for what was randomized is much larger than what we actually measured. So in both cases so far, in our 2 iterations, our 2 simulations, our 2 randomization events, we saw something that was more extreme when it was measured than when we resampled and randomized those data sets. We can do it a third time. And what we're doing when we do a permutation is we're just keeping score. So now we have our third case where our p-value is much larger than what we measured, and our simulated t-stat is much smaller than what we measured. So for now 3 times in a row, what we measured seems to be more extreme than what was randomized. Well, that's great. Now, if we do that enough time, we can really gain a lot of confidence in terms of whether our measurements tend to be more extreme or more randomized than what we would get based on a simulation. But doing this by hand, you can just kind of see. I mean, this is 3 times, and you got to do it like 5,000 times, 10,000 times. That would be very, very slow process. One, you got to go into Excel, and you got to actually create all of those. And then you have to go back in here, and you have to actually run each test. Further, and we haven't even done this yet, you got to keep score each and every single time. Right now, we're 3 for 0. Every single time, our measurements are more extreme. But maybe after 100, we get 99 that are more extreme and 1 that's not. Well, we keep having to do that, keep having to do that. That seems tedious. There's a pro. There's a solution. And it's actually really straightforward. So let's actually create a new file. And let's get our data. And I'm actually just going to get our original data. I'm going to copy that. And I go into our new script. Okay. And now we're going to add a package. Coin. Coin is a package that does a very good job with 2 sample permutated tests. The other package we'll use a lot for permutation is called lmperm. So I'm just going to put 2 sample permutated tests. And everything about what we do is the same. So, let's actually run through the previous script and get rid of everything because we don't want it anymore. And now we're going back to our new script, and I'm going to save this as, and let's save this as butterfly permutated. All right. Again, we need to load coin. We could load car if we want. We could load tidyverse, but we load coin. We don't have to do any simulations by hand, so I'm just going to load our original data, butterfly edge. We get our summary, and again, we still have to fix habitat, that's fine, but we already have the code, so it's not a big deal. So we run those lines, we do summary, and we now have attach. Okay, now I'm going to put this down for a bit because we really don't need to worry about that. And oh, hey, here's a big one. You do not have to worry about normality. Don't matter. So you can ignore tests for normality with a permutated procedure. Doesn't matter. Permutations analyze data relative to measured distribution. So your data's distribution is the distribution you're comparing against, which is great. So we're going to ignore all that stuff. Awesome. We're not going to do a t-test. No. In fact, what we're going to do is we're going to do a permutate t-test. 2 sample t-tests. The code is very similar with a few caveats. One, this is a one-way underscore test, and that is key. Again, these things have meaning. If you put one-way dot test, that is a different test and it will not function properly. If you put one-way underscore test, then it will function properly. Now, we're in good shape. We've done all our simulations. We've actually got our information. What we now need to do, though, is we need to define the distribution. Again, for a parametric test, the distribution is a normal distribution. For a permutated test, we have to define it. So what we're going to do is we're going to create an approximation of the distribution. Basically, we're going to create thousands upon thousands of individual tests based on a Monte Carlo approximation. And in this procedure, we're going to do that 10,000 times. 10,000, 5,000, those tend to be good, robust. Anything above 10,000, one is overkill. Two, it can slow your computer down. I had a student one time that said, I'm going to be cheeky. I'm going to do 1,000,000. And we just sat there for minutes upon minutes waiting for that computer to process. 10,000 times, 5,000 times, perfect. So we have this one little line of code. We go back into here, we can hit comma, we can hit that, we get rid of our parentheses, and how many times are we going to resample? We're going to resample 10,000 times. We get a result, we get a p-value that says 10 to the negative 4. We get a z-value. We don't get a t-stat, we get a z-value. And the reason we get a z-value is because a z-test is the test you do when you have the entire population. So when you measure everything, you do a z-test. When you have to sample out from the entire population, you do a t-test. A t-test is sort of compromised. When you do a z-test, you don't report degrees of freedom because there are no degrees of freedom. You're not doing that. You're not sampling out. You're doing everything. And therefore, all you have is really the z-value and the p-value. Now, you might be asking yourself, why are we able to do a z-test? Well, the reason is because you are sampling out the entire population. You have done 10,000 iterations of randomized efforts. And in that, more than 10,000 of them, your sample was more extreme than what you could generate randomly. So when you report it, I tend to like to report the z-stat. I like to report the n-value, how many samples I have, and you report the p-value. You can then actually run your graph and you can do your charts, and the only thing you would have to do now is put in an appropriate result sentence. In that case, I might put something along the lines of butterfly biodiversity was higher in hedge habitats than interior habitats. And then I would put down my evidence. I'll put down z equals, and what was my z? 0.59 and 40 and p less than that. And there you go. Y'all have a good afternoon.